Hello, everyone. Welcome back. And today we're going to be talking about definite integrals. Now, earlier on in calculus, we discussed taking antiderivatives and indefinite integrals. Now, antiderivatives essentially are the opposite of a derivative. So to take a derivative, we do the opposite to take an antiderivative. Now, this is a little bit more complicated because we're looking at a set of bounds where we're taking the area under a curve over two respective bounds, as shown by this little symbol here, a and b, with b being our upper bound and a being our lower bound. Now, our function f of x is what we're taking the integral of, or the antiderivative of, and dx, this is very important. This helps symbolize what variable we're integrating with respect to. When you go further into calculus, we will be doing multivariable calculus, and it will be far more complicated in understanding which of the respective variables you're actually taking the integral with respect to. So this is very important in the long run. And on the right-hand side here, I've kind of shown the steps to take when dealing with definite integrals. The first one is pretty much the big one. You have to integrate the function with respect to the d term and then paying attention to what variable comes after the d. Now, this is easier said than done because integrals can become far more complicated as we go further on in calculus, but in Calc 1, you'll be dealing with either simple trigonometric functions that you've seen the derivative of, so you can go backward to find the antiderivative, or functions such as e, natural log, the square roots, or just simple polynomial functions. And then our second step here will be plugging in the upper and lower bounds into the integral that we've solved and taking the difference, so f of b minus f of a. And I've shown these two steps in this example here, where we have the function x squared, and we're taking the integral of it between the bounds 1 to 2, the variable with respect to x. Now, we all know that this is a parabola. I will draw a small parabola here. I apologize if it is a crude drawing. I'll do my best. And then we could say 1 and 2. So we are looking to solve for this area here. Now, without an integral, this would be extremely hard to take the area of because it is not a square or a rectangle, something we can easily take the area of. It has a bit of a curve here that bows, so we're going to be using an integral. Now, as I've said before, we kind of know that we have to find something that when we take the derivative of it, we're going to be getting x squared. Now, looking at this, if we have 1/3 x cubed, if we drop this 3 down, that'll be 3 over 3, which will be 1. And then 3 minus 1 will give us 2. So we will end up with x squared. So we know the integral of x squared will be 1/3 x cubed. And once again, this is a definite integral, so we need to be paying attention to these two bounds, 2 and 1. So what we're going to be doing is plugging in 2 and 1 into the x variable here. So we'll be getting 2 cubed minus 1 cubed, and we have to divide both of those by 3. Now 2 cubed is 8, and 1 cubed is 1. 8 minus 1 is 7. 7 times 1/3 will give us an answer of 7/3. Now, once again, this is a fairly simple example of an indefinite integral, but it helps symbolize all the steps that you need to do to go through. And one other useful thing to note is that we did not add the symbolic plus c constant term. That is because we are dealing with a definite integral, and we aren't, there is no potential variation in the answer because we are paying attention to a respective bound. So when you are dealing with an indefinite integral, where depending on your bounds or where you're taking the function with respect to, the constant term would change, but not with definite intervals. Okay, so I hope this was useful in helping you learn definite intervals.